Let's finish up Chapter 10. In this segment, we'll cover the other three methodologies for evaluating investments, then look at some special cases, unequal lives, economic life, and finding the optimal capital budget. In Part A, we noted two things about internal rate of return. It has some flaws, but it is preferred by executives. Modified internal rate of return, MIRR, addresses those flaws, giving executives a good percentage return. While this slide explains MIRR, much like valuing a non-constant growth stock, a chart is worth 1,000 words. This chart shows how MIRR is calculated for Franchise L. All outflows, negative cash flows, are discounted to times 0. All inflows, positive cash flows, are future valued to the last year. Both ends are summed. This gives you the present value and future value to use in your calculator or in Excel. The sum of the inflows equals the terminal value. In this example, we only have one outflow, the $100 it cost. Once we have the sums at each end of the timeline, we can easily solve for modified internal rate of return. This slide shows using a formula. We'll see the calculator solution on coming slides. So how do you easily find the future value of the inflows without having to future value each one individually? The TI Business Analyst 2 cash flow worksheet does not do future value of an uneven cash flow stream. The Pro version does. But you can find it with a couple of extra steps. Step 1. Enter only the positive cash flows in the cash flow worksheet and find the NPV as usual. Step 2. To easily move the solved for NPV to the PV-TVM key, press CE/C to exit the cash flow worksheet. 118.78 should still be displayed. Press the plus or minus key to change the sign. Press PV to place the value in the PV cell. Enter the rest of the variables. N is the number of years of the project, 3. IY is the discount rate, 10. Payment is 0. Press compute and future value. Future value of the cash flows is 158.10, which is now already in the FV cell, which is where you want it. Be careful if there's more than one negative cash flow in the cash flow stream. If so, the negative cash flow must be discounted back to times 0 and added to the initial outflow. Also, when entering the cash inflows in the CF worksheet for Step 1, the negative cash flow must be accounted for by entering a 0. Step 4, we now have all the variables to find the modified internal rate of return. Simply use the TVM keys as shown and solve for IY, which will be the modified internal rate of return. Fortunately, there are two ways to find MIRR in Excel. If you do all the prep work to find the future value of outflows and the present value of the inflows, then the rate function in Excel will work just like the TVM keys. But Excel has an MIRR function, shown above. Note that the MIRR function asks for two rates, a financing rate, which is the discount rate, and a reinvestment rate, which is the future value rate. For all our examples, these will be the same and equal to the cost of capital. This does solve the internal rate of return's reinvestment rate assumption problem. We'll see how it handles the multiple answer problems on later slides. The profitability index is closely related to NPV. It measures the dollar return per dollar of investment, bang for your buck, so to speak. We've already seen how to arrive at the net present value of Project L. It's $18.79. So ignoring the cash flow 0 cost of $100, the present value of the inflows must equal 100 plus 1879, 118.79. Profitability index is computed as shown above. Project L returns $1.1879 for every dollar invested. Project S returns $1.1998. The profitability index can be useful when capital is rationed, but you can't rank mutually exclusive projects using PI. Probably the easiest to understand and possibly the oldest evaluation method is the payback period. Payback is the number of years it will take to recoup the initial investment. Using Franchise L, this demonstrates the method. First, accumulate the cash flows. Find where the sign changes from negative to positive. In this case, the project pays back between years 2 and 3. In finance, recall that we generally assume that cash flows occur at the end of the period. In this case, we assume that they occur evenly throughout the period. That allows us to figure out how far toward the end of year 3 we need to go to exactly pay back the initial $100 investment. Payback is equal to the last year with a negative cumulative payback, that would be 2, plus the absolute value of the last negative cumulative cash flow divided by the next inflow, or the absolute value of minus 30 divided by 80. So 2 plus 30 divided by 80 is 2.375. Following the same method for Project S finds a payback of 1.6 years. Payback is very easy to calculate and to understand, and it does provide some indication of risk and can be an important measure for startup firms where liquidity may be critical. But there are problems with payback. It ignores time value of money, which is pretty fundamental in finance. It ignores cash flows after the payback period, which biases it against projects where the cash flows grow over time, like Project L. The choice of a cutoff for acceptable payback is arbitrary. The main problem is it asks the wrong question. We're looking for investments that increase the value of the firm, and payback tells us how soon we'll get our investment back. Important information, but not what we're looking for. Discounted payback solves one of the flaws in payback. Follow the same procedure as with regular payback, but discount the cash flows before you accumulate them. Note that the sum of the discounted cash flows will always equal NPV, a useful check on your calculations. There's a video tutorial covering the calculations of NPV, IRR, Profitability Index, Payback, and Discounted Payback posted with this unit. And there's a separate tutorial covering Modified Internal Rate of Return step by step, which is also posted. In Part A, we discussed normal versus non-normal cash flows, but we'll review the definitions here. Normal cash flows means a negative outflow in year 0, followed by a series of positive inflows for the rest of the term of the project's life. Non-normal cash flows involve more than one sign change, meaning more than one negative cash flow over the life of the project. The issue is that internal rate of return can result in multiple answers if the cash flow stream is non-normal. NPV does not have a problem with non-normal cash flows. This project is detailed in the mini case. It involves a World's Fair Pavilion project that will cost $800,000 to build. It's expected to bring in $5 million in year 1, but it'll cost $5 million to put the land back as it was. 2 negative cash outflows. Using the cash flow worksheet, you can find an NPV of negative 386,777, but you may not even get an IRR result, depends on your calculator, or you may get 25%. It's a pretty high internal rate of return for a negative NPV project. If you graph this project, you could find an IRR of 25%, as we did, or one of 400%. 25% is unreasonably high. 400% is ridiculous, so we clearly have a problem. At very low discount rates, the present value of cash flow 2 is large and negative, so NPV is less than 0. At very high discount rates, the present value of both cash flow 1 and 2 are low, so cash flow 0 dominates. Again, NPV is less than 0. In between, the discount rate hits cash flow 2 harder than cash flow 1, so NPV is positive. Result, 2 internal rates of return. The reason you can end up with more than one internal rate of return is that you're solving for the root of a polynomial of degree n. According to Descartes' rule of signs, you can get one real root for every sign change. The rest are imaginary. 2 sign changes, 2 real roots. With non-normal cash flows, MIRR is the technique to use to find a rate of return. I especially like this example because it makes it clear that all negative cash flows are discounted to the left. All positive ones are future valued to the right. An MIRR of 5.6% is more consistent with a negative NPV. So should we accept the project? Not using traditional evaluation methodologies. Consider, however, the firm might decide that the exposure value of having the pavilion is worth the $400,000 loss. They might proceed for strategic rather than financial reasons, but they would know what the cost was going to be. Do you think McDonald's going into China was a positive NPV investment at the start? Probably not, but the company decided it was worth it for the long-term potential. We'll use the 2 mutually exclusive projects shown above to examine the problems involved in evaluating projects with unequal lives. T is a 2-year project, F is a 4-year project. Doing a straightforward NPV analysis on both would lead you to choose Project F, the 4-year project. But there are other ways to analyze this decision. The equivalent annual annuity approach, EAA, gives us a different view of the 2 choices. In both cases, the present value is minus the NPV calculated on the previous slide. FV is 0, N is the number of years of the project, and you solve for payment. Viewed this way, T is a better project. But what if you could repeat Project T for another 2 years, making its life equal to Project F? This is called the replacement chain approach. Replicating Project T for another 2 years leads to an NPV higher than F's original NPV, so T is the better project. Using either approach, the NPV of Project T is larger than Project F. What if you can replicate Project T, but the cost to restart it in year 2 has gone up to $105? Just that $5 change flips the NPV comparison back to favor Project F. Typically, when physical assets are involved in a project, the analysis assumes the project will be run for the physical life of the equipment. This is not necessarily the best choice. On the next few slides, we'll look at alternatives to running a project for the full life of the equipment versus closing down early and selling the equipment for its salvage value. Here are our sample cash flows. The assumption will be that to terminate the project early in any year, you recognize the operating cash flow for that year and the salvage value at the end of that year. Here's how the cash flows for each year of the project, assuming termination of that year, play out. Calculating the NPV for each row will lead us to the best number of years to run the project. The NPV for each choice makes it clear. Best option is to run the project for 2 years, shut it down, and sell the equipment. Conclusion: engineering, or physical life, does not mean it's the best economic life. Our final topic relates to choosing the optimal capital budget. As the slide states, finance theory says accept all positive NPV projects. The cost of funding is built in. But firms may not choose to follow this for 2 reasons: the increasing marginal cost of capital and capital rationing. We've seen in our calculations that raising outside funds incurs flotation costs, relatively low for debt and preferred, but pretty high for new equity. In each case, the cost of that capital component rises, driving up the overall cost of capital. Large capital budgets can be perceived as risky, also driving up the cost of capital. And we'll see how this works on the next slide. Suppose we have $700 worth of projects with positive NPVs, but we'll need to go outside to fund them, and the resulting cost of capital will rise from 11 to 12.5%. If we stay at or below 500, we won't need outside funds, so our cost of capital will be 11%. If we elect to go with the $700 budget, then all projects must be evaluated at the 12.5% rate, which may cause some to fall out. This is an iterative process to arrive at an optimal budget for a firm. The other issue is capital rationing. Firms may choose not to fund all positive NPV projects for internal or external reasons. Internal reasons would be that the firm simply places an upper limit on the amount of capital it wishes to invest in a given year and advises each division how much they can spend. This is soft rationing. If a division came up with a blockbuster project, the firm would probably find the funds. Hard rationing is enforced by the market in the sense that the market will not provide any more funds to the firm through stock or bonds. This is a very negative situation for the firm. This concludes Chapter 10. In Chapter 11, we'll address estimating the cash flows for a project,